Hello friends, welcome. In this video session of heat transfer, we will start unit number 3, which is related to convection. In this video lecture, we will learn about continuity equation, momentum and energy equation. My name is Mr. S.V. Kumbar, Assistant Professor, Sharad Institute of Technology College of Engineering, Yadra, Ichalkaranji. So today we will start with continuity equation in Cartesian coordinate that we had already learned in fluid mechanics subject. Now consider a fluid element. We can also call it as control volume, that is parallelepiped with sides dx, dy, dz as shown in figure, and this dx is parallel to x-axis, dy is parallel to y-axis and dz is parallel to z-axis. Now consider rho is the mass density of fluid at a particular instant. U, V, W, these are the velocity along x, y and z direction respectively. Now first of all consider phase A, B, C, D. Now rate of mass of fluid entering through phase A, B, C, D, we call it as fluid influx, is equal to density multiplied by velocity along x-axis and multiplied by area. Generally we calculate mass flow rate by the formula density multiplied by area multiplied by velocity. So similarly here density multiplied by velocity along x direction is u, and area of ABCD is, as it is a rectangle or square, so its area will be dy multiplied by dz, which is multiplied here. So rate of mass of fluid leaving phase EFGH, which is also called as fluid efflux, is the same mass will leave, and in addition to this the rate of change of mass with respect to x, that is rho into u into dy into dz plus dou of dou x into rho into du u into dy into dz into dx, which is nothing but dm, that is rate of change of mass. Now the net gain in mass per unit volume along x-axis due to flow is nothing but difference between equation 1 and equation 2. So subtract equation 2 from first, this term will get cancelled and which is remain only, that is minus dou of dou x, this term in negative sign, minus dou of dou x rho u dx dy dz. Now from this equation dy into dz is taken outside, because as one of the rule of derivative or integration is that if one constant term is present, we can take either inside or outside the derivative term. So this product remain constant, take it outside. So mass accumulated per unit time due to flow along x direction is minus dou of dou x rho u dx dy dz. Similarly, we can calculate mass accumulated per unit time due to flow in y direction as minus dou of dou y rho into v here, right? Because u is the velocity along x-axis, v is the velocity along y-axis. So minus dou of dou y rho into v dx dy dz, and similarly mass accumulated per unit time due to flow along z direction is calculated by referring this equation minus dou of dou z into bracket rho into w dx dy dz. So as I told you, these are the two equations we can get. Now total gain in fluid mass per unit time for fluid along three coordinate axis as summation of these three equations. So minus dou of dou x rho u plus dou of dou y rho v plus dou of dou z rho w into dx dy dz, right? Let's say this is equation number 6, and the rate of change of mass of the parallel pipe, that is control volume, is dou m upon dou t, and mass is calculated by density multiplied by velocity, because density is nothing but mass per unit volume, therefore mass is equal to density into volume. So dou m upon dou t, mass is replaced by density into volume, volume of parallel pipe is dx into dy into dz. So replace that term, and here the gain of fluid mass per unit time take place. That's why we have to equate these two equations, because this is also rate of change of mass of parallel pipe and this is also net of gain of mass per unit time. So equating these two equations, we will get minus dou of dou x, this term as it is, minus dou of dou x, rho u plus dou of dou y, rho v plus dou of dou w, rho w into dx dy dz is equal to this term as it is, dou of dou t, rho into dx dy dz. Again you can take this as common, because it is one of the rule of derivative or integration is that if any term is constant you can take it outside. If you take this term outside, this dx dy dz will get cancelled. So only this dx dy dz, this dx dy dz will get cancelled. Only dou rho upon dou t will remain here on right hand side. So take this term to right hand side, we will get dou of dou x rho u plus dou of dou y rho v plus dou of dou z rho w, plus this term is taken to left hand side, or either this term is taken to right hand side, plus dou rho upon dou t is equal to 0. So this equation is known as continuity equation in three-dimensional form, and it is applicable to any type of flow, whether it is a steady flow or unsteady flow, whether it is a compressible flow or incompressible flow, right? Now if the flow is steady, then generally all fluid properties remain constant with respect to time. So dou rho upon dou t is equal to 0 for steady flow. And if it is an incompressible fluid like liquid, then rho is constant. So again this rho can be taken outside, and this equation is reduced for steady and incompressible fluid as dou u of dou x plus dou v upon dou y plus dou w upon dou z is equal to 0. This is a reduced form of continuity equation in Cartesian coordinate that we had already studied in fluid mechanics. Also, continuity equation is the product of cross-sectional area of the pipe and the fluid speed at any point along the pipe, that is constant. That is, product of area into velocity is equal to constant, which is nothing but discharge. So this product is equal to the volume flow per unit second, or simply flow rate, and mathematically it is represented as area into V is equal to constant, which is nothing but Q is equal to A into V. Now continuity equation derivation. As we had already studied this derivation, consider a pipe through which fluid is flowing. Let's say A1 is the cross-sectional area at inlet, V1 is the velocity of fluid at inlet, A2 is the area at outlet, V2 is the velocity at outlet. So by applying continuity equation, discharge remain constant here. Whatever amount of fluid flowing through this pipe, Q remain constant. Therefore Q is equal to A1 V1, which is equal to A2 V2. This is continuity equation. Now if rho is the density of fluid, then mass of the fluid contained in the shaded region at lower end is given as delta m1, that is the small amount of mass flow rate density into volume, and this density into volume is area into v1 into delta t, where delta t is small amount of time. Now the mass flux is defined as mass of fluid per unit time passing through any cross section at lower end, that is delta m1 upon delta t is equal to rho 1 a1 v1, and mass flux at lower end, that is nothing but rho 1 a1 v1. Similarly you can get mass flux at upper end at rho 1 rho 2 a2 v2. Since the flow is steady, that is fluid properties remain constant with respect to time, and the density of fluid between the lower and upper end of the pipe does not change with respect to time. Therefore rho 1 a1 v1 is equal to rho 2 a2 v2. This is simplest continuity equation you can apply in any fluid mechanics related to problem, or If you want to apply in convection, you can apply this equation, and in general form we can write it as rho AV is equal to constant, and this relation describes the law of conservation of mass in fluid dynamics. That is, mass cannot be created nor it can be destroyed, but the total mass of the system remain constant, and if the fluid is incompressible, then the density is also constant. Therefore, rho 1 is equal to rho 2. So rho 1, rho 2 will get cancelled. Therefore, we will get A1 V1 is equal to A2 V2. That is continuity equation in simplest form. This is continuity equation that we had already studied. Summarizing all terms in previous slides, we will get dou rho upon dou t plus dou rho u upon dou x plus dou rho v upon dou y plus dou rho w upon dou z is equal to 0. Now in vector form, we can write it as dou rho upon dou t plus divergence of rho u which is equal to 0, where dou rho upon dou t is nothing but change in density with respect to time, and divergence of rho u is nothing but net flow of mass across boundaries in convective term. For incompressible fluid, dou rho upon dou t is equal to 0. So alternatively, we can write it as dou u upon dou x plus dou v upon dou y plus dou w upon dou z is equal to 0. Now, already in fluid mechanics, the analysis of motion is performed in some way that by using Newton's law of motion. Generally, we had applied Newton's second law of motion. And what was that second law of motion? The rate of change of momentum is directly proportional to the applied force. That was Newton's second law of motion. Therefore, F is equal to ma, right? Now, in fluid mechanics, it is not clear what mass of fluid we should use a different form of equation. Means which force is responsible for the motion, whether gravitational force is responsible, whether pressure force is responsible, whether force due to viscosity is responsible. That's why here Newton's second law of motion can be written as the rate of change of momentum of a body is equal to the resultant force acting on body and take place in the direction of force. So F is nothing but summation of all forces, right? So momentum is equal to mv. The total force exerted on fluid in a control volume in a given direction is equal to rate of change of momentum in the given direction of fluid passing through control volume. That is nothing but F is equal to m dot V out minus V in. So mass flow rate is given by density multiplied by area into velocity, and area into velocity is nothing but discharge. So we can write this equation as F into rho q V out, that is velocity at outlet minus velocity at inlet. And here this F is considered as F1, which is nothing but resultant force, force exerted in the given direction on the fluid by any solid touching the control volume. F2 is nothing but force exerted in the given direction on the fluid by body force, that is gravity force. F3 is the force exerted in the given direction on the fluid by fluid pressure outside the control volume. So F is nothing but summation of all forces. So total force is nothing but Fr plus Fb plus Fp. So this F is nothing but summation of all the forces which is causing the motion. Now application of momentum equation. Now we will consider a few examples below. First one is the impact of jet on the plane surface. Now whenever any fluid, either water or steam, when enters through nozzle, a jet is formed. When that jet forms on either plane surface or curved surface, we can apply this momentum equation. So impact of jet on plane surface, this is the first application of momentum equation. Second application is force due to flow round a curved vane. As I told you, when a jet of water or jet of steam enters on curved vane, that is curved vane of turbine, then there is a momentum transfer takes place, and that's why turbine rotates, and here heat energy is converted into mechanical energy, or force exerted by water or steam is converted into mechanical energy, and in this way momentum equation is applied. Third application is force due to flow of fluid around a pipe bend. Now you might have seen pipe bend or pipe elbow in fluid mechanics. Now whenever any fluid flows along elbow or pipe bend, it exerts force on bend. So that force can be calculated by applying momentum equation. So while carrying water from dam for drinking purpose, generally we have to use large elbows or bends in that piping section. So in that case, we can calculate the force exerted by water on bend, right? While designing that pipe structure, we require that force. Next application is reaction of jet. Now you might have seen launching of satellite. So in that launching of satellite, the reaction obtained by that jet is calculated by momentum equation. So last equation is energy equation. So by Newton's second law of motion, F is equal to ma. Now if we consider x direction, so Fx is equal to mass into acceleration along x. But in fluid flow, this force is that is Fgx plus Fpx plus Fvx plus Ftx plus Fcx, where Fx is the total force or resultant force, Fgx is the gravity force along x-axis, Fpx is nothing but pressure force along x-axis. So x denotes this is the direction, G denotes it is the force due to gravity, P denotes force due to pressure, V denotes force due to viscosity, T denotes force due to turbulence, and C denotes force due to compressibility. Now, if we assume a flow to be ideal, then equation first becomes Euler's equation, that is dP upon rho plus G dz plus V dV, which is equal to 0, that we had already studied in fluid mechanics. Just this is the revision. This equation is known as Euler's equation of motion, as in the form of differential equation. Now if you integrate this Euler's equation, we will get Bernoulli's equation, which is known as energy equation in fluid mechanics, and it is based on law of conservation of energy. So if you integrate this equation, we will get P upon rho plus G into Z plus V square upon 2G, that is P upon rho G plus Z plus V square upon 2G. This equation is known as Bernoulli's equation of motion, that is energy equation, and we can apply this Bernoulli's equation anywhere. So whenever fluid is flowing, now consider previous application. We had studied continuity equation in simplest form, that is Q is equal to area into velocity. If you want to apply this Bernoulli's equation in that pipe, we will get P1 upon rho g plus V1 square upon 2g plus Z1, which is equal to P2 upon rho g plus V2 square upon 2g plus Z2. But this equation is used for ideal fluid. Now ideal fluid is that fluid where viscosity is 0. But in nature, such fluid does not exist. But under some circumstances, we can assume water or air as ideal fluid. In general, nature, real fluids are present. Now this equation is modified as P1 upon rho g plus V1 square upon 2g plus Z1, which is equal to P2 upon rho g plus V2 square upon 2g plus Z2 plus HF. So what is the difference between this equation and this equation? Only HF term is present, and this HF term is nothing but head loss due to friction. In a real fluid, viscosity is present, and viscosity means resistance to flow. One layer of fluid glides or slides with another layer. That's why, because of fluid friction, some head loss takes place, and that HF is considered in this equation. So this Bernoulli's theorem is first derived in 1738 by Swiss mathematician Daniel Bernoulli, and this theorem states that the total mechanical energy of flowing fluid, comprising the energy associated with fluid pressure, the gravitational potential energy of elevation, and kinetic energy of fluid in motion, remain constant, which is related to law of conservation of energy. Energy cannot be created nor it can be destroyed, but energy can be transformed from one form into another form. That is the sum of pressure energy or pressure head, kinetic energy or velocity head, potential energy or potential head always remain constant. Means this is sum of all energies, this is also sum of all energies, but this is sum of all energies at point 1, this is sum of energy at point 2 for ideal fluid, and for real fluid sum of all energy, which is equal to sum of all energy at point 2 plus HF. Why HF is added to second term? Because fluid flows from point 1 to point 2, therefore head loss due to friction has to be added in the second part of term. So this is end of continuity, momentum and energy equation. So thank you very much.